Hi, everyone. This is your I can't believe we're panic buying toilet paper physical chemistry instructor, Dr. Hopkins. Uh, this is the second part of our discussion, our first discussion about multi electron atoms, building on what we did with helium. So, we're primarily been focused on helium, atomic structure. So, now that we've done the Pauli exclusion principle wavelengths, so the ones that are antisymmetric with respect to um, pairwise permutations for the ground state for helium, why don't we try the first excited state just for the heck of it? And so what we'll do is we'll have our same 4 2-electron spin functions from the previous video. So if you didn't watch that one, then you're kind of behind. And we're going to use those. And then let's look at the orbital function. So the electronic configuration, first excited state would be 1 electron in the 1s orbital. Then the next highest orbital is 2s, correct? So it would be 1s1, 2s1. And so if we were to write this in the formalism we've been writing this, our two wave functions here, psi in the middle of the page, are 1s1, 2s2. So put the first electron in 1s, the second in 2s. But we know that they have to be indistinguishable. So our second electron could actually be in the 1s, and our first electron could be in the 2s. So both of those are answers. So basically what we need to do is make a superposition of that. And just like we did with the spin functions, we can make a superposition at the bottom where we add and subtract. Now I'm not bothering with the normalization. We'll not worry about it. We'll just assume it's normalized. And so which one of these would be the antisymmetric orbital function? Well, obviously, when you add them together, just like we did with the spin functions, the addition of those two are symmetric, okay? So if we wanted to make a total wave function that is antisymmetric, we have to use the antisymmetric spin function that we used for the ground state. And then the second superposition of the orbital states, orbital functions, is where we subtract our two, and it's antisymmetric with respect to the pairwise permutations, just for the same reason that the spin function was before. So you can see, and you may have to wrestle with this to show where you're flipping the ones and twos around to show that it's actually -1 in front of this instead of +1, but it's antisymmetric. So we can combine with, because antisymmetric times antisymmetric is equal to symmetric. Symmetric times symmetric is equal to symmetric. So the only way to get a total wave function that's antisymmetric is to have symmetric with antisymmetric. So if we have an antisymmetric orbital function, we can combine it with any of our symmetric spin functions. Okay, so that means we get 3 of them because we had 3 symmetric functions, if you recall. So we had the one positive superposition spin function, which we showed here, which had spin up, spin down. Then we have the one that's both spin up, and then the one that's both spin down. And so in this case, we have 4 properly symmetrized wave functions in the first excited state of helium. So what that represents is we've got, since the electrons aren't in the same orbital, right? If we're following along back to our general chemistry thing, this understanding, since we're occupying 2 different orbitals, the electrons can have any spins they want. We don't have to worry about making them anti-parallel. And so this is a representation of that. So in the 0th order model, which we're still kind of working in, there's basically a 4-fold degeneracy. If you remember back in the previous video, all of the energies are only dependent on the ends. And if we're in the same 2 ends, so 1s and 2s, then the total energy would be the 1 over n squared for the 1 and plus the 1 over n squared for the 2, and you would add that up and get some value. But all would be the same. So regardless of whether we started with the psi plus or the psi minus, so depending on which is which has the orbital wave function as symmetric versus antisymmetric. So we'd have a 4-fold degeneracy. There'd be no difference. Now, if we were to allow, so now we're going to start thinking about what happens. We know that the 0th order model is not going to work. We know it overestimates the energy by quite a lot. So what happens if we allow our electrons to interact? So let's allow electron-electron repulsion to take place. Well, in that case, we lift that degeneracy, and basically we'll get a threefold degeneracy with the psi minus. So those are where we had symmetric spin functions, and that's what we would call a triplet. So we would have a triplet state, and then we would have the psi plus, which there was only one of them, is a singlet state. And so this is no longer the 0th order model, but it is still approximate. And actually, if we explain kind of that process, if we go to the next slide here, we have developed, those wave functions that we're writing when we write out the R and Y for each individual electron associated with it, these are 0th order wave functions. We haven't developed those wave functions based on interactions between the electrons. Okay, so the true Hamiltonian in this case is just the 0th order Hamiltonian plus this new term, right? Where the H0 is our 0th order Hamiltonian, or our operator. Psi 0 is not an eigenfunction of it's only an eigenfunction of the 0th order Hamiltonian. We can solve that, but it's not an eigenfunction of the overall Hamiltonian. And we know, based on what we learned at the beginning of the course, if we have something's not an eigenfunction, if we want to evaluate it, we have to evaluate an expectation value. And so what I've shown in the middle of this page is the expectation value for the energy, assuming that psi 0 is normalized. If it wasn't, we would have a denominator with psi 0, psi 0. So there you have the formalism. And if we split those out into the 0th order wave function, or the 0th order expectation value, and the potential energy between the two electrons, we get a 0th order energy, because that's the eigenvalue. And then we still have that term with the potential energy between the two 0th order wave functions. Our E0 is, as you recall, around minus 10 times 10 to the 6 joules per mole for helium, for the ground state, remember? And then the other value, since it's an electron-electron repulsion, it will actually reduce the binding energy, which is actually, if you think about it, back to the experimental value, our experimental value was much less than our 0th order value. So if we're reducing it, we're coming closer to getting to the right energies. But the problem is that integral, that psi 0 v psi 0, is non-trivial to evaluate. All right, so that brings up a little bit about kind of the methodology to how you would actually solve these, or one methodology to solve these difficult problems. So we have these non-trivial integrals that we have to deal with. So how would you solve this? In one way of solving the Schrodinger equation, using the variational method. Okay, now I'll let you know first off, the variational method we don't do on a piece of paper. We let a computer do this. We let a program, an algorithm, solve these kinds of things. But it's a better approximation model by numerically solving in an iterative approach towards the actual value. Okay, so just like we saw in the 0th order model, the approximate energy is always going to be greater than the actual energy. Okay. So we're always going to overestimate the binding energy. So in the variational method, we can use a trial function, and the trial function can be anything. Okay, it can be hydrogen-like functions, it can be Gaussians, it can be any kind of wave function that is well behaved. So kind of going back again to the beginning of the course when we talked about what a well-behaved wave function is, that has these variable parameters. So we'd have, and I've just listed, I've got phi here and n1, n2, however many parameters you want to evaluate to your function. But these are things you can adjust to adjust the value of that wave function. So we put in that that trial function, and then we minimize the expectation value by varying the parameter. So we let a program vary the parameter, test whether did it go down, did it go up. And then what happens is it searches around, and eventually you'll find, if you find a global minima, because the expectation value is always greater than or equal to the actual energy, you'll be closest to the actual value. Okay, so that's kind of a methodology to approach the right answer. And this variational method is not just for atoms, it's also for molecules. So this is, now we're in kind of the computational approach, because these are problems that we can't solve. So when we go to the next video, we'll do is a little bit different way of representing the zeroth order wave functions for atoms. So until next time.